In this video, which is another dealing with mechanisms in AS organic chemistry, we're going to look at the free radical substitution reactions. This looks at alkanes reacting with halogens under the influence of ultraviolet light, and also the decomposition of ozone. Remember, a radical is a species with an unpaired electron. So a species means it could either be an atom, a molecule, or an ion. And we show the unpaired electron with a dot on the relevant atom. Okay, so this reaction is mediated by ultraviolet light. You can do it at higher temperatures, above 300 degrees, but usually we just want the examiners just want you to say ultraviolet light. You can use chlorine, bromine, or even fluorine. Okay, it's a substitution reaction because if we look at this scheme here, one of the hydrogen atoms is being substituted for a chlorine atom. Hence we get hydrogen chloride as a byproduct. So it is a substitution reaction. The mechanism. Okay. The mechanism is split into three stages. It's unusual. It's nothing like the other. Mechanisms we've seen because it doesn't involve curly arrows. Now, there's one initiation step, two propagation steps, and three termination steps. So, to help me remember this, I remember that this mechanism involves IPT, easy as 1, 2, 3. So the initiation step. In this reaction between methane and chlorine, the chlorine-chlorine bond is the weakest, hence this breaks under the action of ultraviolet light. And this forms two chlorine radicals, and we show the radical with the dot. Now, the chlorine radicals then go on to the propagation step. So the first step involves the other starting material reacting with a chlorine radical to form the byproduct, which is hydrogen chloride, and a methyl radical. So chlorine radicals come along, it's taken a hydrogen has taken one electron with it, and it's left carbon with its electron. And so we show that the electron's on carbon by putting the dot on the carbon, not next to the hydrogen. The second step involves this very reactive methyl radical, or any alkyl radical, which reacts with another molecule of chlorine. This methyl radical now takes a chlorine atom to form our desired product, which is chloromethane, and leaves us with a chlorine radical. So overall, if you look at these two steps, we start off with the chlorine radical, we finish off with the chlorine radical. It is this is catalytic in chlorine radicals, this reaction. The termination steps. Now, termination steps involves any two radicals combining together to form a molecule. So here's one option: is two methyl radicals combining to make ethane. In the exam, just write it as CH3CH3. That's the exam board prefer. Another combination would be a methyl radical reacting with a chlorine radical to make chloromethane, so we can make our desired product here. But most of it is actually formed during the propagation steps. And finally, two chlorine radicals could come together to form a chlorine molecule. However, this poses a problem, because chances are your reaction mixture will still be under the action of ultraviolet light. So this means that more chlorine radicals can be formed and then react. Now the trouble is that you get to a certain point in your reaction and you don't have much methane left, but you've got a high proportion of chloromethane here. So a chlorine radical is more likely to encounter a chloromethane molecule, therefore it takes a hydrogen atom away from chloromethane, goes through the propagation steps again to form dichloromethane. Dichloromethane molecules can also react further to make trichloromethane, also known as chloroform, and even go all the way to tetrachloromethane. Okay, so that's the simplest version of this free radical substitution. Okay, now the other version we've alluded to is with CFCs and ozone. So chlorofluorocarbons catalyze the breakdown of ozone. Now ozone is this strange looking molecule with the formula O3. It has a wonderful effect because it protects the Earth from the high energy UVB UVC radiation. Unfortunately, CFCs, chlorofluorocarbons, were found in the 1970s to be causing the breakdown of the ozone layer. And so we've taken, so the world's taken actions to phase out CFCs to help the ozone layer to regenerate, because in this stratosphere, ozone breaks down to an oxygen molecule and an oxygen atom, but these will automatically recombine to form ozone molecules. So first of all, let's look at this mechanism. We don't really have a termination step here, but we do have an initiation step. We have one initiation step. So any chlorofluorocarbon, our CFCs, under the action of ultraviolet light, we break the carbon-chlorine bond. This is the weakest bond, and we're left with a chlorine radical and an alkyl radical. That's the best way to term it. So our chloro-difluoro-methyl radical. There are two propagation steps. So the chlorine radical now goes to react with the ozone molecule, and this takes an oxygen atom away and leaves us with a molecule of oxygen. The chlorine-oxygen radical can also react with another molecule of ozone to form two oxygen molecules and a chlorine radical. Okay, now if we look at these two reactions being combined, and you can do this for any sequence of reactions which are related, if you add them together and then cancel down what's on both sides of the equation, so there's a chlorine radical on the left hand side, there's a chlorine radical on the right hand side, so we could get rid of them. There's a ClO dot here and the ClO dot on the right hand side. We can get rid of them. So ultimately we're left with two ozone molecules breaking down to give one oxygen molecule and two oxygen molecules. So overall, two ozone molecules make three oxygen molecules, and so the chlorine radical catalyzes the breakdown of ozone to oxygen, and just one single solitary chlorine radical can catalyze the breakdown of about 100,000 ozone molecules. So it's quite destructive. Okay, there are alternatives out there to CFCs, but these are found to be greenhouse gases, so they are not greenhouse gases which are more dangerous than carbon dioxide, so they're not used in refrigeration. And then the final ozone reaction, the final reaction using radicals is that nitric oxide or nitrogen monoxide is a radical. It's formed naturally in the air, generally under the course of lightning or high energy, so nitrogen reacts with oxygen, and that will catalyze the breakdown of ozone. as shown in these two equations. Okay, thank you for watching.